Alright, so far we've talked about dipole forces, or dipole-dipole interactions, and we've talked about hydrogen bonding. These are examples of intermolecular forces, and both of these rely on a molecule's partial positive being attracted to a partial negative of a neighboring molecule. And so we saw a picture like this when we were talking about dipole forces. The hydrogen is partial positive, the chlorine is partial negative. A different separate molecule also has a partial positive and partial negative, and the attraction of these two molecules is that intermolecular force. You can see that essentially what's happening here is that the attraction is between something that is positively charged and negatively charged, not full positive and full negative, but partial positives and partial negatives. This explains how we see liquids and solids in substances that have dipole moments, in things that have inpolar molecules that are samples of substances, because since there is this force of attraction between neighboring molecules, as long as we get to low enough temperatures, this force of attraction causes the molecules to come closer and closer to each other and therefore condense into liquid if they were in the gaseous state, or even freeze into the solid state. Again, as you get low enough temperature, take away enough energy, get down to a low enough kinetic energy, that these forces of attraction cause the particles to be held rigid in the solid. But what about substances that are nonpolar? What about molecules that do not have a dipole moment? For example, let's take a nitrogen molecule, N2. Nitrogen is a diatomic element. That means there are two nitrogens. If we think of their Lewis structure, they happen to be bonded by a triple bond, and each nitrogen does have a lone pair. But as you can see, this is a totally nonpolar molecule. If I have a sample of nitrogen, I've got a bunch of these nitrogen molecules all floating around with no partial positives and no partial negatives. So what on earth would cause nitrogen, N2, to ever go out of the gas phase? And then my next question is it always a gas? We know at room temperature, nitrogen is a gas. But is there any temperature where nitrogen is a liquid? And absolutely there is. There is liquid nitrogen. This exists at very, very low temperatures. You're talking about in the order of around negative 200 degrees Celsius, nitrogen is going to be a liquid. Now, we actually can't get cold enough for nitrogen to become a solid, but in the liquid state, we know that the particles are very close together. So what is it about nitrogen that's causing there to be an attraction between the nitrogen molecules that would cause them to want to get close together and be held there loosely in the liquid state? It's not partial positives and partial negatives from a dipole moment, because nitrogen is nonpolar. So what is it about nitrogen that causes it to condense into a liquid? A nitrogen molecule has a triple bond, and each nitrogen has a lone pair, but in general we see a perfectly symmetric molecule for nitrogen. So I'm going to replace our Lewis structure with sort of a region of space. Here is the nitrogen molecule. It is three-dimensional, although I'm working on a two-dimensional sheet of paper. It is a three-dimensional structure. It's roughly spherical. And what we have in this spherical region at the very, very center, down here, really, really minuscule, are the nuclei for the nitrogen. That's where the protons and the neutrons are. And recall from our discussion of what an atom looks like, this takes up a very, very, very small amount of space. The rest of the space of this molecule is electrons. These are the electrons in the electron clouds for nitrogen. We know that they're in orbitals, and we know shapes of orbitals, but that's not important. Let's think of it as a roughly spherically symmetric region. Those electrons are moving. They are moving around the respective nuclei as well as between the nuclei. That's what attracts these two nuclei, is the bonds. Those are the electrons that are being shared. But at any given instant, there might be a buildup of more electrons on one side of the molecule than on the other. So at any given instant, there could be a temporary, instantaneous dipole moment for this molecule where the side that has the buildup of electrons would be partial negative, the side that has the depleted number of electrons, because they've all moved over to the right-hand side in my picture, has a partial positive. We call this an instantaneous dipole, and we know from our experiments that this is going on in molecules. Even molecules with permanent dipoles, polar molecules, exhibit this behavior. So we get what's called an instantaneous dipole, and all of the molecules in our sample are doing this. So we've got a bunch of molecules of nitrogen, and at any given instant, one of them might show this instantaneous dipole moment, which is going to influence neighboring molecules. So this neighboring molecule might see this partial negative charge, and then it would produce, or would be produced on it, an instantaneous dipole moment based on the attraction to the neighboring molecule. So at any given instant, we see these attractions happening. We call this an induced dipole attraction. The induced dipole attraction, we'll sometimes say it twice, just like we did with a dipole. We will call this an induced dipole intermolecular force. This is an intermolecular force. It is a force between molecules that aren't necessarily polar. They don't have to be polar. And it is based on an instantaneously induced dipole moment just due to the movement of the electrons in the electron clouds. As you lower the temperature on a sample of nitrogen that looks like this, again, you're slowing the molecules down, and these induced instantaneous dipole moments are more likely to influence neighboring molecules. Once you start slowing them down enough, these are going to influence neighboring molecules, and you'll get this chain reaction of a bunch of molecules lining up and being attracted to each other through these induced dipole moments. Now, just as quickly as these induced dipole moments occur, they also break, and so we see these happening and then unhappening over and over again. But this force of attraction is enough to cause nitrogen to actually condense to be a liquid. Now, in nitrogen, the induced dipole moments, the induced dipole attraction is not very strong, and that's why you have to cool this down to almost negative 200 degrees Celsius in order to condense gaseous nitrogen into liquid. But for something like iodine, which is the I2 molecule, which again looks very similar to N2 except for there's only a single bond, an I2 molecule, iodine, diatomic, two iodines, totally symmetric, totally nonpolar. This molecule also has the same thing happening with induced dipole forces, and for iodine, you don't have to cool it down very far in order to get it to be a solid even. In fact, at room temperature, iodine is a solid. That means its boiling point is well above room temperature. It's up close to a couple of hundred degrees Celsius, and in fact its melting point, in order to get it to go from a solid to a liquid, is above 100 degrees Celsius. So even up to the temperature of boiling water, iodine is still going to be a solid material because its forces of attractions between two adjacent iodine molecules are strong enough that even at relatively high temperatures, especially if you're comparing it to N2, it's going to be in the solid phase. There's enough attraction between neighboring I2 molecules to cause those two molecules to want to be very close together and held rigidly in place in the phase of the solid. So what's the difference between nitrogen and iodine? Why is N2 a gas at room temperature? And why is I2 a solid at room temperature? It has to do with the number of electrons. If we look at a periodic table, each nitrogen has 7 total electrons. And so a nitrogen molecule would have 14 electrons. If we look at the periodic table, iodine has 53 electrons, so an I2 molecule is going to have 106 electrons. There are way more electrons in this cloud around the I2 nuclei. Way more electrons means the greater potential for this instantaneous dipole, which means the greater attraction to neighboring molecules, inducing dipole moments in neighboring molecules, and the stronger this force of attraction is. So the bottom line is, let me squeeze it in here, the more electrons a molecule has, the stronger the induced dipole forces. It turns out that all molecules, even those that have dipole moments, honest to goodness legitimate dipole moments, also will have induced dipole forces, and this holds true. The more electrons there are, the stronger these induced dipole forces are going to be, which means the more likely that substance is going to be in the solid phase or the liquid phase as opposed to the gaseous phase. All right, to wrap up these induced dipole forces, we have another way to name them. These are also known as London dispersion forces. Another name for instantaneous dipole forces or induced dipole forces is London dispersion forces. And just to make matters more complicated, sometimes we simply refer to them as London forces. So if we are referring to the forces of attraction, the intermolecular forces of attraction between molecules based on induced dipole moments due to instantaneous dipoles being formed from the electrons in the molecule, we will often refer to them as London forces or London dispersion forces or induced dipole forces. And so you will hear them referred to all of those different ways.